So then we'll continue with our next talk, which is by Xiangyu Cao and atom cavity scramblers and low-rank Sachdev-Ye-Kitaev models.
Thank you. Thank you all for coming. We're ready to speak for a second time for GeoFlow collaboration. So I'm going to talk about scramblers and SRK models. And so there will be two parts. The first part is about this experimental proposal and this experimental theoretical collaboration between Berkeley and between Stanford and Berkeley, which is already published. And so I think Greg has already talked about this work during one of the previous meetings. So I'm going to be a bit brief on this. Then I will talk about follow-up work, which is a theory paper that we just put on arXiv last week, and it's done with Ehud and Jae Kim, who is a grad student who's sitting over there. Okay, get started. So one of the goals of this collaboration is to make a black hole in the lab and to study it in the lab. So here's a famous picture of a black hole. Now, it's an astrophysical object, difficult to realize in the lab. However, for our purpose, what we care about the black hole is that it is actually a fast scrambler. Moreover, what makes it even more possible to realize in the lab is ADS-CFT holography. Instead of building gravity machines, we can actually look for quantum mechanics models which scramble fast. And however, this is not easy to find. It's not easy to find such a model, and it took a genius like Kitaev to find such a model. And here is such a model. It's an auto interaction model with a bunch of a large number of Majorana fermions with random interaction. And what he showed precisely is that his model is the fastest scrambler that can ever exist. Namely, it saturates the famous Mandelshein-Schenker bound on chaos or the exponential growth of the Epsilon exponents. Okay. However, this model is not called Kitaev model, but Sachdev-Ye-Kitaev model for a historical reason, which is that the model actually was already studied in a slightly different form. It can be written as a random Heisenberg magnets with random auto interaction between spins, and these spins are SUM spins. And Sachdev-Ye and also later George Harcole found a trick to solve this model in the large M limit, n being the size of the group. And what they did is that they can map this model to this fermion model by basically representing a spin by a fermion bilinear, and then this coupling matrix of spins become schematically the coupling matrix of the fermion bilinears. Okay, so what is this? What can we say about this model compared to Sachdev-Ye-Kitaev? Well, one thing we can say is that this model seems to be easier to realize in a lab because it's a magnet. So it's in principle possible. And actually it is possible. And one way to do it, figured out by our AMO colleagues, is that we can put atomic spin in an optical cavity, and let the optical mode, like the photon mode, mediate interaction between atomic spins. Since these optical modes are delocalized in the whole cavity, the interaction does not care about the distance between the spins. So we have realized auto interactions crucial for fast scrambling. So here is a cartoon picture. You have cold atoms in optical cavity, and they have interactions mediated by the photon mode. Now, in reality, what our Stanford experimental colleagues have realized is a similar but the model with more details. And what And one crucial detail of this model is that there is only one optical cavity coupled to these atoms. And as a result, you get not this generic all-to-all random magnet, but a magnet with a special kind of interaction. So here, let me just run over this Hamiltonian. So this is the Hamiltonian with SU2 spins, and you have all kind of exchange interactions, x, x, y, y. These is like XXD model, and we can tune this delta parameter. Now, what is different about this model from this model is that this matrix, which are highlighted here, is a separable matrix. So in other words, it's low rank. The coupling matrix has rank 1, basically. Now we may ask, what is the consequence of this low rank? This is the main goal of this first theoretical experimental paper that is just published, and the conclusion is that low rank means slow scrambling. So here's the summary of the results in terms of a dynamical phase diagram, if I can use this term. So what we have two knobs. One knob is the isometry anisotropy delta, and the other knob is the spin, is the representation of the spin. You can have spin 1/2 up to spin infinity. Now, if you look at this diagram, we first find that in fact there are two integrable lines, which give you exactly golden Richardson type integrable models. So at least, so already here there's no chaos, there's no scrambling. Now at large spin, in the classical limits, there is some classical chaos, but the thermalization is nonetheless slow. Furthermore, if you look at the most quantum case of this model, there is a new type of integrability which we call integrable star. So what is integrable star? So let me first describe our method that we use to find this integrable star. Our method is a kind of universal spectroscopy method based on analyzing experimental or numerical data. So basically, you give me some numerical or experimental measurements of expectation value, then we can basically do a Fourier analysis of that, spectral analysis of that data, time series data, and separate slow from fast operators. So imagine that you have measured some expectation value in time of some spin bilinears, and then we can tell from these data that you can have conserved spin bilinears, slow spin bilinears, and a fast spin bilinears. So the conserved ones, their autocorrelation never decay. The slow ones, they decay, but they don't decay to 0, and they have a plateau, and the fast ones, they decay very fast. So the result, as I said, is that we have found an extensive number of slow two local operators, which means spin bilocals. So here we have a system of just 10 or 13 sites, I don't remember, and we can find as many slow operators. So our interpretation of this result is that there actually exists an extensive number of almost two local integrals of motion. So think of operators which are almost two local, but you have some dressing terms of higher number of body terms. So this is what we mean by integrable star. It's a new type of integrability. It does not require fine tuning, and it seems to require disorder because you have these random coupling constants, but it's also different from the many-body localization in that you don't live in one dimension. It's actually multiple. So okay, so this is the summary of this atom cavity paper. If you have questions, okay. So let me move on. So we have seen that rank 1 doesn't cut it. If you just have such a low rank randomized, you won't get faster scrambler time. So how large a rank do we need to have faster scrambling? So here I draw an axis of ranks. Here is our atom cavity model, and here are these SYK models and the SY magnets. They have high rank. But let's ask what is the rank of the coupling matrix? So actually it's not that obvious. So if you look at this model, you have n spins, so your matrix is n by n matrix. It's a generically random matrix, so it has rank O n. However, if you look at the SYK model, as I said, you have to think about this JIGKL as a matrix with ij as one index and kl as another index. So I and j runs from 1 to n, so you have an n squared times n squared matrix. So the rank of this coupling matrix is n squared. So it's unphysically large compared to this this magnet that we can in principle realize in a lab. So the origin of this is the large m limit here. Basically, this m here is technically the m of the spin here, but somehow this is forgotten in the history as Kitaev reinvented this model. So history aside, we have now two questions. Okay, what is the minimal rank for fast scrambling, and also this rank seems unphysical. Can we study some SYK model with a more physical rank ON?
Why is it unphysical?
It's you start with this model and you say okay, let me study this large M limit which can solve. But by doing so, you have changed the rank of the coupling matrix from an extensive rank to a super extensive rank. And as I will show, the physics at extensive rank is quite different from super extensive rank. So this is the reason. This is the reason I suspect that this change is not that innocent. So, but let's keep moving, and we can discuss this in the end. Okay, good. So the motivation now is that I want some model like SYK, which is that's solvable, but in which I can also tune the rank. So this model can be written down as such. So instead of having a full random JIGKL matrix, I would just write this matrix as a rank R matrix just by writing its spectral decomposition. You write just a rank R matrix, and R can be tunable, and you can tune it to the scale in different manners with respect to the system size. So here there's an alpha which tells you how it scales with the system size, and there's also a prefactor. Now you can also tune the spectrum, so given by lambda n's, to any distribution that you like. Finally, the angle vectors are random. This idea. I'm going to do it. So a diagram of this low rank SYK is like this. Instead of having a 4-body interaction, you just decouple it to 3-body interaction. So this we didn't write down this model as first person to write down this model. It has been written down before for different purposes, and the motivations were mainly condensed matter. In my knowledge, there are two groups of people who wrote on this specific case of this model before us. So one of them is Santa Barbara's group by Chen Ke and Zhen Bi. They want to study instability of SYK non-Fermi liquid against low rank perturbations. And the other more recent paper came from Stanford. Thanks PGE. So they wanted to study Cooper pairing in a non-Fermi liquid in a electron phonon model. So okay. So you may ask, okay, this I understand. It's basically it's a special case of our model, but why is our model the same as and they are electron phonon models. So here's the answer, and it's also the exact solution method of this model. So basically, you can write our model as a sum of squares of random fermion bilinears, and then to solve it, you just Huber-Stanovich decouple it, and so you introduce these bosons, and these bosons are really the same as the bosons in the electron phonon model. These phonon bosonic modes, up to some details that won't change the IR physics. So once you do that, you can go through this large machinery, and you can write down Schwinger-Dyson equations for your fermion Green function and boson Green function, and they can be. I don't need to write them down. I just need to draw some diagrams. So a fermion is the fermion free energy is like this. So you have it's stressed by a boson, and the boson Green function looks like this. It can fork into two fermions and merge again. So if you stare at this for a second, you will realize that what is the dominant physics of this model? It is actually hiding in this boson diagram. So if you write down this boson propagator, you will see that it has this form, and the denominator is dangerous. It can vanish. So when the denominator is small, we can call these boson modes soft modes. So these soft modes dominate the low T physics, and they may also condensate, like in both Einstein condensate. And when they condensate, if you look at this diagram, it condensates, so has a vacuum expansion value, and you get say two-body SYK2-like terms, which is relevant because it's quadratic, and it also breaks time reversal symmetry. So a good analogy is BEC. If you just open the textbook, you will find this formula of boson occupation numbers, and we know from these textbooks that the phase diagram of a Bose gas depends on the dimension. Why? Because it depends on the density of the soft modes. And here we have something very similar, where the density of the soft modes is given by the density of these lambda n's, which is something that we can tune. So we should expect that not only the rank matters, but also the whole distribution matters. So now let me show you the main results, since these methods are quite straightforward. First, how does the rank matter? And this has been partially figured out in these earlier papers that I quoted. What we know is that if you have a sub-extensive rank, which means the rank is much smaller than n. Oh, let me start from super extensive. So you have a super extensive rank, much larger than n, then you get back exactly S1K. And you can understand this from the diagram. So you basically what happens is that this bosonic line becomes equivalent to this two fermion line. You get this Malone diagram of usual S1K. And on the other hand, if you have a sub-extensive rank, then what happens is that this Bose-Einstein condensation physics will dominate. And at a low temperature, you will have only a Bose-Einstein condensate, and it generates a purely quadratic Hamiltonian. And you will have basically a free-forming model with no scramblers. Now, clearly, what's interesting is this extensive region. So what we first found, and also these authors also found, is that there is a crossover temperature. So as high enough temperature, you are still SYK, but as you go below this crossover, you will have new quantum phases. So what are these quantum phases? They are actually richer than we expected. You have a full classification table of 4 universality classes just hidden here. So why are there so many classes? Why is there this duality? Because the spectrum of this rho lambda plays a crucial role in the low temperature physics at the extensive regime. So more precisely, all of the spectrum doesn't matter. Only the right edge of the spectrum matters. So I point out here. So if I go from this direction here, I have 2 classes of SYK faster scramblers, defined by a maximal Lyapunov exponent, And they have a distribution which is either completely negative or with the delta peak at the maximum. Then for more generic distributions, like semicircular or an inverse semicircular, we have non-maximally chaotic, which we call almost the fermion liquids, because here the fermion dimension is that of a fermion liquid. However, they are almost the fermion liquids, but not quite, as we will see in what sense. So I will go through these four classes in more detail. Now, if there's something that catches your eye in this table, please ask now. Yeah.
So are these? I forget which one, but are either the first or second one kind of similar to this strange metal?
Sorry.
Are either the first or second one kind of similar to strange metal? Are they also almost strange metal?
I would say strange metals are more like, so strange metals are more like these classes which have no quasi-particles. So they have quasi-particles, but their quasi-particles are just spoiled. The quasi-particles decay too fast to be a fermion liquid. So I wouldn't say they are strange metals. They are less strange metals than strange metals, but more strange metals than fermion liquids. Yeah.
Can I think of this as the distribution of modes inside the cavity?
Right, exactly. So yeah, so this is lambda is the square of the coupling strengths of the modes. So like more. So basically, it's a very good question. If you think about cavities, you should bar this guy. So in cavity setting, lambda is the square of coupling, so you don't have negative lambda. So you have these. Okay, good. So let me make a remark on something which looks innocent. It's the scaling of the Hamiltonian. So I wrote on that Hamiltonian, but I didn't tell you how you put prefixes in front so that it has correct thermodynamic scaling. So if you think about it, actually there are two ways of doing it. First, you can ask, I want extensive energy at finite temperature. Second, I want well-defined dynamics at infinite temperature, which is what we did in the atom cavity paper. We studied only infinite temperature dynamics. So they will give you different criteria for normalizing the Hamiltonian. And what we find is that for this low rank SYK model, they agree only in the super extensive and extensive regime. So when the model looks more or less like SYK, but they don't agree in the sub-extensive regime, where the infinite temperature dynamics is parametrically slower than the finite temperature dynamics. So this actually has already been noticed in this original atom cavity model, which could have been a warning sign that this is not a fast scrambler. Okay, now let me go through these classes a bit more carefully. So first, these fast scramblers, and they are not only fast; they actually realize QSYK for any real value of Q. So why is that? So first, in terms of Bose-Einstein condensate analogy, there's no Bose-Einstein condensate because you have so many soft bosons. So it's like in zero dimension. You cannot. There's no one mode that you pick out to condense. And here there's simply nothing that you can condense. And then the fermion scaling dimension depends continuously on the rank over n, so the reduce the rank in thermodynamic limits. And you can realize any 1 over q, which is the scaling dimension in QSYK model from q to 2 to infinity more or less. And if you want q equal to 4, you just go to large rank. And if you go to small rank, you can either go to a free fermionic like delta equal to 1/2 or delta equal to 0. And there's an analytical formula for that. And there's also a so-called supersymmetry. The boson dimension is related to a Fermi dimension by the exact formula. And finally, the string adjacent equations are conformal invariant, and we believe that they are reparameterization invariant. Why do we believe so? Because we have calculated the Lyapunov exponents by following Kitaev's approach. We look at ladder diagrams and we look at their angle functions and angle values, and we find that the angle value of the ladder diagram is 1 exactly when lambda L is 2 pi t. So it's maximally close, like in SYK. And the angle function is also that SYK is basically the same scales. So all of this indicates that class and 3 and 4 realize QSYK model with physical microscopic parameter, no fractional. And okay, this is just for fun. These formulas are quite this. So okay, let me move to class 1 and 2. So just a reminder, these classes are characterized by a non-delta peak edge on the right, and it is characterized by power law. So for class 1, you have a positive power law, and for class 2 you have a negative power law. And we don't want too large power law because it will look like too much the Fermi liquid that we don't but care. So first thing that I want to show is that you have a fermion-like spin dimension, and a simple argument is that you start from class 3, so you add artificially a delta peak, and then you let it go, and you look at this diagram, and you look at this dot, and you see that it will go to delta equal to 1/2. And physically, what happens is that you have Bose-Einstein condensation in both classes, and the detail is that class 1 is more like Bose gas in D larger than 2, so you have a vanishing density of state. So you have a condensation at finite T. In class 2, it's like D smaller than 2 Bose gas, so you don't have condensate at finite T, but you still condense at 0 T. So in the end, you still have this physics. You have a condensate, and it generates quadratic term, and it gives you this delta. However, this is not all. Although there are quasi particles because delta equals to 1/2, their decay rate is anomalously fast. So the decay rate of the quasi particle frequency omega goes like omega to the power of 1 plus eta, which for eta smaller than 1 is much larger than omega squared, which is the Fermi liquid behavior. So what happens is that your fermion is dissipating into this path of bosons, and you have a non-analytical density of bosons of soft bosons. So you have an anomalous decay rate, and you can think of it as in terms of subohmic dissipation in class 1 and super-ohmic dissipation in class 2, where the density vanishes or diverges respectively. And this has some consequences. For example, it leads to the anomalous specific heat in class 2. You can show that it's not linear in temperature as usual. It's larger, parametrically larger than linear in temperature at low temperatures. So this also has consequences for scrambling. So here we don't have these coordinates formulas because we cannot produce them. It's even more involved than that, because you cannot just use the conformal limit to calculate the lambda L. You need to go to the subleading level, which encodes exactly these decay of quasi particles. And we did some estimates of power quantity, and we found that lambda L is like T to the 1 plus eta, which is still faster than a Fermi liquid scrambler in class 1, and in class 2 actually we expected to behave linearly in T, although it should not saturate always the universal bound. So this is a recapitulation that these 4 classes actually exhaust all the possible non-trivial behaviors because they basically grow from this tree. You just decide you like, and you have the distribution, and you have your corresponding lot of properties, and they are, just to emphasize again, nothing is Fermi-liquid, and basically this class is the most Fermi-liquid-like, and these classes are the most non-Fermi-liquid-like, the fastest scramblers. So I think it's time to wrap up. Yeah. So conclusion: scrambler needs higher rank, and most importantly, in the extensive regime, which I argued is physical from the point of view of random Heisenberg magnets, the spectrum of the coupling matrix plays an important role, and we expect that this is relevant for SUM random magnets away from the large M limit, and we would like to study it further. And just to relate to the first part of the talk, in the second part we worked at low temperature, and it will be nice to see what we can say about infinite temperature dynamics, such as slow operators and integrity star. And finally, for high energy people, we suspect that class 3 and 4 have the Schwarzian, although we don't know how to find the soft mode action. And also more open question: do these almost Fermi liquids, which also scramble quite fast, have a gravity rule? And finally, our model completes the studies from studies Schmalian on superconductivity, and our results extend their normal state result, and we would ask what is the fate of the superconductivity from our 4 classes in normal states. So with this, I would like to thank you for your attention.